Hi everyone. Today we have breaking news, and Marina, she's presented us a recent work from the MAGIC telescope. Every one of you knows Marina. She's working here at the ISC, and let's see what is this MAGIC discovery that she will present today.
Okay, thank you very much, Salvatore. Sorry for the delay. So I'm going to talk to you about this press release we had some days ago, last week, and this press release was based on a new article published by the MAGIC collaboration. So we will talk about very high energy emission at the cosmic gamma ray horizon, and yes, it's a very long title, but I will tell you about everything. A MAGIC discovery happened thanks to gravitational lensing. Okay, the title is very long, but the two important things I want to tell you today, because the seminar will be very short, a breaking news of 20 minutes. The two important points are those one. First, that this emission was detected at the cosmic gamma ray horizon. It means very, very far away, at the limit of the possibility of detection for this kind of telescope. And the second point is that this discovery has happened only thanks to gravitational lensing. And now I will go on explaining you what I mean with these 2 points. So first point, this very high energy emission was detected at the limit of our possibility with MAGIC telescopes. We are talking about this concept of the gamma ray, cosmic gamma ray horizon. I like a lot this description of the horizon, of the possibility we have to see our very high energy photons. Okay, I will remind you that what MAGIC telescope can see is emission coming from very far galaxies at a very high energy. So what that means? It means that we are not looking at the emission you can see with normal telescopes, radio, optical, and so on. What we are looking at is high energetic particles produced in very high magnetic fields, in the very high, in very huge accelerators in distant galaxies. So at the end, these very high energetic photons to come through this long way to our telescopes, they suffer of a lot of processes that don't happen in normal, I mean, in the other energy bands. For example, what we have very high energetic photons, they can interact with the extragalactic background light, and in this interaction they lose a lot of energy. So what we see at the end is a reduced emission, very difficult to detect, and this of course doesn't happen in the other energy bands, in the optical or radio, or okay, the other energy bands, they have other problems of course, but not this specific one. So for us, the cosmic gamma ray horizon is something real. I mean, it's something that measures the possibility we have to look to these photons. We have like this wall, we can call it a wall, and beyond that, we cannot detect anything, because these very high energetic photons coming from high redshift, they cannot reach us. They lose their energy before reaching the Earth. So this theoretical concept, this horizon we have, this limit, was shaped by theoretical physicists working on gamma ray telescopes. And you can see there at the left the theoretical models. What they say, okay, they work on very complicated formulas, because this horizon is made by a lot of variables. Inside there are cosmological variables like you know, everything you need to model the cosmological universe. So the Hubble constant and a lot of things there, and also the sensitivity of the telescope. So this formula is made also by the energy threshold of our telescopes. It's a very complicated thing. And I mean, this theoretical model can predict very clearly that behind a given redshift, it will be impossible for a Cherenkov telescope to look at this emission. And on the right, we have a graph of this cosmic gamma ray horizon measured, because it's not only a theory, but it's something that we can measure. So we can measure the difficulty we have at looking at cosmic gamma rays coming from very far galaxies. Okay, so long story short, this means that the limit for us was set as something like redshift 0.6. So since we knew about these studies, we knew that it wasn't very easy to look at a redshift that was more than 0.6. Okay, what happened is that we could go farther than 0.6. We could detect the last year, I mean the detection happened in 2014, but we could analyze data from two sources. We discovered two sources in very high energy, which redshift is very close to 0.1. So we were very surprised because we thought that we couldn't go so far away. But as was predicted by these theoretical models on the cosmic gamma ray horizon, is not only this horizon is not only dependent from the energy of the photons, but also from our sensitivity. So since the last years MAGIC had a major upgrade, this sensitivity increased so much that we couldn't expect to reach such a very important limit. So of course, if some of you is working in radio and in optical, a redshift like that can make you laugh because it's nothing. I mean, you can reach farthest distances, of course, but for a Cherenkov telescope, this is like crazy. We were really excited about that. So the two sources we discovered with MAGIC are those two in red. One, I already gave a seminar about that because we published an article the last year, but the one I'm talking about you right now is the other one, QSO B0218, that is the farthest one, 0.94. So I will talk you about this source that is very special because, as I anticipated you, it was discovered thanks to gravitational lensing. These are just the two astronomer telegrams we sent when we discovered these two sources. Yes, we are very proud of this because it was a really nice discovery. Two very nice discoveries. Okay, I think all of you know that the MAGIC telescopes are Cherenkov telescopes, so they work in the optical in the sense that they can detect with those mirrors there. The Cherenkov light that is in the optical is a blue light, but this Cherenkov light that we detect is coming from the showers produced by particles hitting the atmospheres. So in some sense it's an optical telescope, but what we see is not in the optical, are directly very high energy particles coming from the distant universe. Okay, not directly the showers produced by these particles, but at the end is that. We can discriminate the particles that we are looking at because they produce a different kind of electromagnetic shower. So it's different to see a shower produced by a gamma ray from a shower produced by a hadron. So since they give us a different shape in our camera, we can easily, okay, not always, but easily discriminate the different particles that are causing the shower. Okay, Cherenkov light, I don't want to talk a lot about it. You know, for sure, it is produced when a particle traveling in a medium is faster than the light. Of course, not faster than the light in absolute, but faster than the light in that medium. So this is what happens in the atmosphere. This particle is very fast, faster than the light would be in the atmosphere. And when this happens, this blue light is produced. It's a very fast blue light, so you cannot see with your naked eye, but it can be seen by the telescopes. Yeah, okay, the telescope, the more you have, the better it is. And this is the sensitivity of MAGIC telescope that is increased in the last year. Will not focus on that. And okay, let's go to the second point of this talk, that is the gravitational lensing help. So, this galaxy is so distant for us. How can we detect that? It's very distant. The signal is very faint. How could you discover a galaxy like that with the Cherenkov telescope? You cannot just go there and survey the sky and hoping that you can see something. In this case, what helped us was the gravitational lensing itself, but also our friend Fermi. There is a satellite surveying the sky, and Fermi already detected these sources in 2012, and they have seen before us that this source was gravitational lensed with these two signals coming from this lensing, and since Fermi was monitoring, Fermi immediately told us when the leading signal was detected by them, so we could follow Fermi. So in radio, this source was well known. You can see here this radio image coming from Merlin array, and these two signals coming from the gravitational lensing. What happens is that you have this source, is very far away, then there is another spiral galaxy very big in the middle, and so the signal, as predicted by Einstein and general relativity, is split in two parts. Because this galaxy in the middle is acting like a lens, a gravitational lens, and the signal is reaches us in two different steps. The first one, that is called the leading trail, and then the second one delayed, in this case of 12 days approximately, then they reached the Earth after the first one, for the effect of this gravitational lensing. And okay, so Fermi detected the leading component. They told us immediately that they got this leading component, and then after 10 days, we start to observe, hoping to see the other component coming. And we have seen that component, and nobody was believing that. We will not believe in that, actually. I was analyzing the data, and we were 3 people analyzing the data. And if we don't reach 5 sigma of significance, we cannot do anything. Our hands are tied. We cannot do anything. So the first guy, he got 3.5. Okay, no detection. The second one, it's like, it's like a joke, the Italian, the English. The Polish guy, he got 4.2, so no detection. Then there was me. It was my first analysis, so I was very excited. And I got 5.2. So the Italian was very lucky that time. It was a detection. And it was incredible because nobody was believing that. It's like 0.1 redshift. How was that possible? Somebody was also saying, okay, but gravitational lensing is not possible. We can see something like that. But no, it was a detection, of course. It was at the limit, very limit of our possibilities. So we had to produce special Monte Carlos. We have to work on the software also. But at the end, it was very clear that we detected that signal. And we were extremely excited about that. There is another image of gravitational lensing. It's a very impressive process. Of course, for me, it's something fantastic, but I think that more of you knows already about the gravitational lensing working with other sources. But for me, it was amazing to see how really we could look at this process happening. And you can also see in this big image, like it's not just the lens, the big galaxy you have in the middle, because the galaxy is made by other stars, of course. So you have a main gravitational lensing, and then you have a lot of other micro lensing there that could influence your signal. Of course, it's very difficult for MAGIC to distinguish between these two processes, but anyway, it's a very complicated thing happening there. Okay, so here I will go through the main results of the paper very fast, because if you have questions, we can talk about this whenever you want. But I don't want to keep it long, because it should be a short talk, this one. So, okay, this was the detection. You can see the significance is 5.7 now, after the final analysis. And here I wrote that we expanded the very high energy sky from 0.6 to 0.94. That was fantastic for us. And then here, another image of the paper. You can see the paper here. The reference is the multi-wavelength light curve we built. You can see there are not a lot of simultaneous observations. So we just have MAGIC in very high energy. Then we have Fermi in high energy. Then we have Swift in XRT. And then we have KVA in the optical. we don't have other simultaneous data. So we had to model the broadband spectral energy distribution using those data only. You know, when you have simultaneous data, the modeling of your source is more easy. When you have data coming from different periods, then it's not very effective. Anyway, using those data, here you can see in Fermi, the light curve just in Fermi. Fermi, they detected this source in 2012, and they could see clearly the two, the leading and the trailing emissions, one after the other. So they knew, they calculated that the time should have been like 11 days, and this is what we were ready to look at them. Maybe you can ask why you didn't look at the first emission, the trailing. Well, we tried, Fermi, they told us immediately, but we couldn't because it was moon time. So when it's moon time, we can observe actually. We have sunglasses, moon glasses for the telescopes, but the threshold is very high in that case. So we couldn't have detected this emission. But okay. So Fermi, they knew what we have to expect. And it was indeed 11 days, like they predicted. So there, this image is coming from the Weber as well, and is the spectral energy distribution. You can see there what we did with the data available. And first we tried with the one zone model, but it didn't work because of the few data. And so then we tried with this other model. It's a two-zone synchrotron model, and it worked better. And okay, of course, this is something I'm not expert in, modeling of sources, but anyway, it's an important result because we are trying to explain where this emission is coming from. And following this model, the emission is coming from a region that is not inside the broadline region. It's something like maybe coming from the jet. Okay, it's hard to tell, but it's important for us to try to figure out what's going on there. Okay, so these are our conclusions. And I want to focus again on the two important points of this discovery for us. Because I know it's not easy maybe for you to understand why this is so exciting. At the end, it's only 0.1 redshift. No, 0.1. It's almost 1 redshift, and it's a gravitational lensed source. And maybe you know a lot of them, and you already have seen them with your instruments. But for us, it's the limit of our possibility. And this means that we can study this cosmic gamma ray horizon and make it better, because introducing the data coming from these far sources, the cosmic gamma ray horizon, can be better shaped because we can measure it again, inserting this new data. And this means that if we can make this cosmic gamma ray horizon calculation better, we can also understand better the cosmological nature of this extragalactic background light that we don't know exactly how it works at so long distances. And the second point is that this is the first and only gravitational lens detected in very high energy. So it was a very important result for us. And yeah, that's all. Thank you.
Marina, for the interesting talk. Any question?
Hi, Marina. Thank you for the talk. Very nice. It's the second time I hear it, but it's okay. What kind of information can you infer from the source with this? In the sense, okay, you've got this camera, you've got this signal. What kind of information can you infer from the galaxy that is emitting it? Or oh, that was not me. It's okay. Yeah, that's the question.
Okay, one of the most important things that you can say from the very high energy point of view is how this extragalactic background light is shaping the distance between you and the galaxy. So this information is not really about the galaxy. It's more about the path the light is doing to reach you. And this we did. We didn't discover anything special about this extragalactic background light source, but we could constrain it. So we could a bit improve the actual models of this extragalactic background light. Okay, we are talking about upper limits, but anyway, for us is an important result because we could go and probe this extragalactic background light for the first time and such a long distances. So our extragalactic background light models, they were not really prepared for that, and now they are a bit better prepared for that. About the galaxy itself, well, having very high energy emission in general, it means that you have a very huge acceleration going on there. And also the fact that we did not observe at the same time optical and radio flare like it usually happens. This could tell us that the emission is coming from a weird part of these galaxies, not from the inner part, but from the jet. So, but you know, it's everything a bit. It's not something I can tell you with some precision.
Other question.
Oh, very nice results. I don't remember if you mentioned it. How large is the lensing magnification? And how do you estimate it?
Well, it was different, this magnification, from 2012, when it was observed in 2012, and when it was observed in this case in 2014. And with MAGIC, we cannot measure this because we couldn't observe the leading signal. With Fermi, it was measured that it was something like 4 times bigger, but it's better if you look into the paper, because now I don't remember exactly. I don't want to tell you something wrong. But in the paper, yeah, we wrote about this magnification because it's important to understand the nature of this gravitational lensing, of course. But unfortunately, with MAGIC, we cannot explore this process.
Okay. Yeah. Thank you.
Others? Okay. So I remember you. Okay, I'm sorry.
Nice talk, Marina. One question. This source is continuous? I mean, if you would observe it again, you would see it again, or is variable?
This source in very high energy, we have no possibility to observe that in a quiescent state because it's too faint for us. It's very at the limit. It's like there is the cosmic gamma ray horizon and the source is there. So we cannot observe them normally, and what we are doing is we have a special monitoring program. Of course, Fermi is helping us because Fermi can monitor easily and more easily than us. So when they catch a flare, they immediately tell us. But we have no hope to see that in a quiescent state, only during a flare. This is why I say we detected only thanks to gravitational lensing, because otherwise there was no possibility to detect that. It's the lens giving us this signal.
Really nice talk. Do you know what causes the different flares in the, because you have the object, you have the galaxy that is lensing that object, what causes the flares? Why you have sometimes more emission and...
Well, the fact is that you have this source is not exactly behind this spiral galaxy, and the shape of the spiral galaxy is not perfectly oval. So what do you have is that the source is a bit further away, and so you have a first signal that is less lensed, so it goes faster, and another signal that has more gravitational lensing, so it goes slower, and it reaches you 11 days later. So it's the position of the source irrespective of the lens. And it's also the possibility that this galaxy, we don't know what there is inside exactly, so maybe there is some micro-lensing going on there, so these signals are not coming together. They have this delay for this reason. Then what produces the flare at the origin, at the beginning? And I have no idea. Nobody knows. Yeah, exactly. Yeah, you only know that after 11 days you have the other signal. No, I don't know anything else. In very high energy, because in radio, they are just looking there and they see the source constantly. And so they have these beautiful radio images. This I don't know exactly what they see in radio, but I think it's not variable a lot. A part of these flares, of course. Yeah. Flare, and then after 11 days you have the other one. Between the first and the second there is a constant period of time. I mean, so far we know it's 11 days, but this is due to the gravitational lensing, you know. It's not due to something going on in the galaxy, in the source. This is just the lensing of the spiral galaxy in the middle. Then what is going on there? The variability of the source. We have a lot of difficulties to see that, because we can detect the source only during this process. So we cannot have a constant monitoring to be able to tell which is the variability in very high energy, because to do that you need to observe for some time, you know, and we absolutely have no possibility to do that. It's too far away for us. This is the frequency between the trailing and the leading and the other image, but the flare itself, I think the last they observed was in 2012. I don't know, because it's modified Julian. The upper one, you say. Well, there's okay. So, but this is what happened in 2012, and they used this sample to define this delay. But what is happening now, in Fermi, I honestly don't know. We follow their trigger, but now I can tell you exactly how frequent are the high energy flares. Yes, this I should check. We should just check what Fermi is publishing about this source. We had other triggers some months ago, so the source is having this flare, this periodical flare, but I don't know more about this periodicity.
Thank you, everyone. And I remember you that 11:30 there is the scientific coffee in the library. Thanks again to Marina.